Good afternoon, everyone. In today's lecture, we learn about carbon NMR spectroscopy under the course of pharmaceutical analysis. So let's start. The chemical shift of the carbon NMR is wider in comparison to the proton NMR. The carbon-carbon coupling is negligible because of low natural abundance of carbon in the compound. Thus, in one type of carbon NMR spectrum, each magnetically non-equivalent carbon gives single sharp peak as does undergo further splitting. So in NMR we have seen the splitting of the peak, but in carbon NMR actually this splitting is not shown, as you know, because of the abundance of the carbon. Okay, low natural abundance of 13 carbon. The area under the peak in carbon NMR spectrum is not only necessary to be proportional to the number of carbon responsible for the signal, therefore not necessary to consider the area under ratio. Proton coupled spectra, the signal for each carbon or group of magnetically equivalent carbon is split by proton bonded directly to that carbon, and n+1 rule is followed. The carbon nucleus is about one-fourth the frequency required to observe the proton resonance. The chemical shift is greater for carbon than for proton due to the direct attachment of the electronegative atom to carbon. So actually during the HNMR, proton NMR, we have seen the chemical shift is between 0 to 12, but in carbon NMR it is from 0 to 250 ppm. Okay, so why carbon NMR is required? Proton NMR is used for study of number of non-equivalent proton present in unknown compound. Carbon NMR can use to determine the number of non-equivalent carbon and to identify the type of carbon atoms which may present in compound. Carbon signals are spread over a much wider range than proton signal, make it easier to identify the count individual nuclei. So in proton NMR, its range was just from 0 to 12, but in carbon NMR we will have a better range, okay, from 0 to 250. That is why you can easily identify the peak. Okay, moreover in proton NMR we have shown integration of different peaks, okay, and also splitting has occurred. And but in carbon NMR only sharp peaks, one sharp peak is observed, and hence your elucidation is better. So chemical shift are measured in ppm from the carbon of TMS. The correlation chart is here divided into the saturated carbon atom which appear as upfilled. Okay, upfilled means it would be near to the TMS. The effect of the electronegative atom would be between 40 to 80 ppm. Then alkenes and aromatic carbon atom should be around 100 to 170. It contains carbonyl carbon bond which appears at downfield from 150 to 200. So how we interpret the carbon NMR? Count many lines, how many type of carbon, then symmetry duplicates give the same line. If there are more carbon in your spectrum, then symmetry appears. Then check the chemical shift window and check the splitting pattern and check the signal height size. So ultimately, it provides information about the number of the non-equivalent carbon atoms in a molecule, the electronic environment of each carbon, then how many protons are bonded to each carbon. Actually, by carbon NMR, we usually focus on the carbon rather than on hydrogen, which is shown in the proton NMR. So this is the basic difference between the proton NMR and the carbon NMR. In carbon NMR, usually we measure from 2 to 220. Sometimes it is 250 ppm. Okay, but in proton NMR, 0 to 12 was the range. Actually, how the shift occurs. Uh, I have already shown this in proton NMR that carbon-carbon single bond would be uh, in the upfield. This is the upfield. This is the lower downfield. Uh, so from 0 to 50 only carbon-carbon single bond. Then uh, ethane group and nitrile group and carbon oxygen single bond would be between 50 to 100. ppm. Then 100 to 150, so the benzene ring would be here, also the alkene ring would be here, that is sp2 hybridized would be between 100 to 150. And finally from 150 to 220, the carbonyl group, you will have some carboxylic acid, aldehyde, ketone, okay, acid and anhydride, you will have this in this location. So this is the basic location of the peak. If you just can memorize this, you can easily understand the availability of peak and nature of the compound. So actually shifts occur due to the hybridization state of the carbon and electronegativity of the group attached to the carbon. So the number of the signal in carbon NMR spectrum gives the number of the different types of carbon atom in a molecule. Actually this is as equal to the proton NMR. Because the carbon NMR signals are not split, the number of the signal equals the number of the line in the carbon spectrum. In contrast to the proton NMR situation, peak intensity is not proportional to the number of the observing carbons. So carbon NMR signals are not integrated. So here, how many uh, environment? Both of them is similar. So we will have one signal. And here you can see we will have two signal. For this carbon, one signal. For this carbon, another signal. So two signal. Okay. So as usual, it is bind with the some heteroatom, then its position would be located within the uh, in the its location would be in the downfield, its location would be in the upfield. Then methyl acetate. Okay, so one carbon, two carbon, and three carbon is present, that is three environment, so three peak will appear, but this three peaks location would be in different place. For example, for carbonyl group, we know carbonyl group locates between 150 to 220, so its location would be in a single sharp peak in where position, in 200. Then it is attached with the co means its location would be from 50 to 100. Okay, then it is cs3 means it would be within 0 to 50. Okay, so position of the signal in contrast to the small range of chemical shift in proton NMR, the carbon NMR absorption occurs over a very much broader range. The chemical shift of the carbon atom in carbon NMR depends on the same effect as the chemical shift of the proton NMR. Actually both of them actually similar, just the range is different. For carbon NMR the range is from 0 to 220, and for proton NMR the range is from 0 to 12. So this is the overall location. I have already shown this. Benzene location would be between 120 to 150, then ethane location would be 100 to 140. Then ethane, this is ethene, and ethane located from 1 50 to 100. Then sp3 hybridized, these are heteroatom, so heteroatom location would be between near to 50. Okay, then ch3, ch bond would be located from 0 to 50. So these are the overall location. So it shows the overall findings. This is the nitrile, its location would be uh, in 100. Then ketone group, I've already discussed that the presence of the ketone group or some other double bond would locate in 150 to 200. Okay, so your ketone group is within the 200, the carboxylic is within 200, so their location is near to the 200. So it has again been shown, also both of them is similar. Just it shows the 0 to 50, so alkyl bond, it shows some uh, co bond, but or cn bond or ccl bond 50 to 100. Then sp2 hybridization 100 to 150, so benzene and ethene would be here, and within 150 to 200 then you will find some carbonyl groups. Okay, now how we will predict the spectra. So for example, in case of carbon NMR, here you can see one carbon, two carbon, there is six carbon here. So how would calculate this? Actually, within the six carbon, this and this is having the same environment. So this is one environment. These and these will have the same environment. So it is one environment. Here is another carbon. It will have another environment. It is one environment, and this is one environment. For four of the carbon, we will have four signal, four peak. Okay, Again, look at this. For here is a carbon, here is a carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon. There is 6 carbon here, but look at their environment. One environment, two environment, three environment, four environment, and look at them. Both of them is having the same environment. That means 5 lines. Then again, look at this. One environment, okay, two environment, three environment. Then look at this. They can rotate. They can rotate in cis trans. Okay, geometrical isomerism. So this would be one. This would be another one. So how much lines? There would be 5 lines. Okay, but here they cannot rotate with one another. That is why both of them was similar, one environment. But here, as there is double bond, we know that double bond can rotate. Okay, so both of them has different orientation. Then again, look at this. So how many carbon are having the same environment? It and this, they are having one environment. Both of them is having one environment. Both of them is having another environment, same environment, and both of them is having another environment. That is 4 environment. Okay, again, we can also see, look at this. Now it is very common that both of them is having one environment, and the remaining 4, these and these, actually these are similar. Okay, because similar group is attached, so we can say 4 of them is having one environment, and the middle 2 is having another environment. So 2 environment will have 2 lines. Okay, so I think you can easily understand how we will predict the spectra. Now look at some peaks. Okay, first of all, tms will be at 0, tetramethylsilane. Okay, now look at the environment. How many environment we will have? Actually, for the benzene ring, our peak appears between 100 to 150. Okay, we already know that for the benzene ring it would be between 100 to 150. Okay, 100 to 150. So in 100 to 150, how much peak we will have? It will based on its temperature, it means orientation. Okay, first of all, it is having one environment, it is having another environment, both of them is having another environment, they are having another environment, and last one is having another environment. So there would be how much peak? There would be 5 peaks. Okay, 1 2 3 4 5, 5 peaks. So one cs3. Okay, cs3 will be located around 0 to 50. We already know that. So this is the cs3. Okay, one carbon has gone. Now look at this bond. Actually, there are 4 environment in the benzene. So 4 environment means we will have 4 peaks. Okay, we will have 4 peaks. So 4 peak will appear in that location. But you can see the last one is deshielded high because it is located within another cs3. Okay, it's deshielded. You can see 4 peaks here, one, another one, another one, and another one. So this is the overall spectra, and this is the solvent peak. Now propanol. So one environment, two environment, three environment. That means 3 environment we will have. Now look at the CO. This bond is CO. Can you remember what is the location of the CO? CO location is between 50 to 100. You know, 50 to 100 there would be one sharp peak. So this is for the CO. Which CO? This is for the CO bond. CO means it is the carbon number C. Then another one is B, another one is A. So A will have the shielding effect, and B will have some how deshielding, and it should be the highest deshielded because of the hydroxyl group. So they are the bond. So their intensity has increased. Okay. So in case of cyclohexanone, as you can see, uh, it would be one environment, both of them would another environment, one environment, another. So 4 peak, but CO, C double bond O. C double bond O means it will have some around 200. So there would be one peak, and rest of them would be around. Then C. So C's location, as it is very close to the carbonyl, it would be deshielded. Then the B, it would be here. Then the A, it would be here. And another one is TMS. Now dihydroxybenzene, you can see uh, the four of them is having the same, because just look at that, you can divide this into plain polarized way. Okay, so these two and this one, only two environment. So one environment is for CO. CO means it would be located around 100 to 120. Okay, and another one is benzene ring. So benzene ring would be 150, around 150. So that is for benzene ring. Okay, this is for benzene ring, and this one is for what? This one is for your uh, CO. Okay, then again phenol group, as you can see here. So how much environment you will have? One environment, two environment, three environment, four environment. So four environment means four peak. So within the four peak, uh, one is CO. CO means it would be around 150 to 200. Okay, so CO is here. Now it's time for benzene ring. The overall ring is the benzene ring. The remaining three would be within the benzene ring. Okay, so the three would have the three peaks. So the three peaks here is here. Okay, and their location as the benzene ring is located near around 150 to 100. Okay, so this three is for the benzene ring and this is for the CO. Okay, now bromocyclohexane. So one environment, two environment, three environment, four environment. Okay, so four environment you will have. Then cyclohexane. So for cyclohexane, how much environment will have? So how it will be divided? One environment, two environment, three environment. So the ethine bond, alkene bond. So alkene double bond would be 100 to 150. So you can see from 100 to 150 there is a bond, and the B would be in the deshielded in that location, and A would be very far away from the double bond. So its location would be here, and CdCl3. This is the solvent used for the NMR spectroscopy, and another one is TMS. Dichlorobenzene. I have already shown this. So in carbon NMR, the lack of the splitting in the carbon spectrum is the consequence of the low natural abundance of the carbon. Recall that splitting occurs when two NMR active nuclei, like two proton, are close to each other. Because of the low natural abundance of the carbon nuclei, the chance of the two carbon nuclei being bonded to each other is very small, that is 0.01%, and so no carbon-carbon splitting is observed. The two features of carbon NMR spectrum that provides the most structural information are the number of signal observed and the chemical shift of those signals. So I have already shown this correlation chart. So here are some disadvantages of carbon NMR over proton NMR. Better separation of the signals and less overlap because it is in wider range. Then uh, signal overlap, easier spectrum interpretation, and direct information about carbon skeleton can be found by carbon NMR. Then simplified spectra, more useful in determining the molecular backbone than distinguished isomer, better differentiation of isomers. Then quaternary carbon, identification of substituted carbon. Then a functional group identification, easier identification of the carbonyl, aromatic and alkene carbon. Then complex molecule, better for large and complex compound. Carbon skeleton elucidation, more suitable for structural elucidation. Multiplicity complexity, easier quick assignment. An equivalent proton issue, greater structural discrimination can be done by carbon NMR. Then branching and substitution pattern, better discrimination of the branching and substitution. The natural abundance, lower abundance minimizes the carbon-carbon coupling and producing the simple spectra. So these are the salient fact about the carbon NMR. So these are the differences between proton and carbon NMR. You can see here. However, there are some problems of carbon NMR, like natural abundance. Carbon 13 natural abundance is very low. Then gyromagnetic ratio. Carbon nucleus gyromagnetic ratio is much lesser than the proton nucleus. Then coupling phenomenon. Carbon and proton have is equal to half, so that coupling between them probably occurs. Then DEPT is a powerful technique in carbon NMR spectroscopy that helps determine the number of the hydrogen atom directly attached to each carbon atom. In DEPT technique, the sample is irradiated with complex sequence of pulses in the bond uh, carbon and hydrogen channel. The result of these pulses sequence in that is that the carbon signals for the carbon atom in the molecule will exhibit different phases depending on the number of the hydrogen attached to the each carbon. This type of carbon will behave slightly differently depending on the duration of the complex pulses. So we can also have the sequence in the similar pattern. So in the similar way, just go through the bond and their peak. I have already discussed this for CH bond. These are the only peaks visible in DPT-90 spectrum. CH2 bonds, CH2 carbons. This appears as negative peak in DPT-135 spectrum, and CH3 carbon. They appear as positive peak in DPT-135 spectrum. So these are the peaks as discussed. So the problem in carbon NMR can be overcome by Fourier transform technique, then decoupling technique like broadband decoupling, of resonance decoupling, and depth decoupling, then nuclear Oberhauser phenomenon. So some decoupling techniques has been shown here, like proton or noise decoupling, of resonance decoupling, and depth. So I have already discussed the carbon NMR spectroscopy determination using depth. So there are some applications of carbon NMR, like carbon NMR is non-invasive and non-destructive method, especially used in repetitive in vivo analysis of the sample without harming the tissues. The carbon NMR of biological material allows for the assessment of the metabolism of carbon, which is so elementary to life on Earth. Then carbon NMR chemical shift ranges to 250 ppm is wider compared to proton NMR, which permits easy separation and identification of chemically closely related metabolites. The low natural abundance of carbon nuclei can be made use of tagging a specific carbon position by selection. Then carbon uh, enrichment, which signals the intensities and helps in tracing the cellular metabolism. Then carbon nuclei are stable isotope and hence is not subjected to danger related to radio tracers. Then carbon NMR techniques is useful for the quantification of the drug purity to the determination of the composition of high molecular weight synthetic polymer. So this is the overall findings from carbon NMR. By this you can easily elucidate structural identification. So here another compound has been shown. So C double bond O for this 180, and C double bond C it is would be 130. Then CH2 CH3 for these two carbon will have on uh, 50. For this CH3 will have 50, but this is a CO bond. Okay, C single bond O. So C single bond it locates between 50 to 100, so it would be in 60. I think you can easily now understand and you can easily identify the compounds. So this is the overall concept from carbon NMR spectroscopy. Thank you.